Right. Our next presenter is Tõnu of Adacor, a sponsor. He will be talking to us on, whoops, my screen changed as I was reading the title. QGenV, harnessing qualified code generator for model verification. Tõnu.
My name is Tõnu, and in this talk I'm going to show you how three important Adacor products can be used together to make better Simulink models and to ensure safety of generated code. At Adacor, I'm responsible for several technologies for supporting model-based software engineering. I'm the technical lead of the QGen team and also member of the lead team for System-to-Software Integrity project. I joined Adacor in 2018. Before that, I've been a team lead for several projects developing underlying technologies for the QGen product since 2006. In this talk, I'm going to give a brief overview of the QGen qualified code generator and then show how two of our verification products, CodePeer and Spark Pro, can be used for verifying Simulink models when coupled with the code generator. QGen is our code generator for converting Simulink and stateflow models to ADA and C code. We have selected Simulink and stateflow features which are unambiguous and safe. We have left out those features which can easily lead to non-deterministic behaviors such as global broadcast in stateflow. The tool supports 120 Simulink blocks most frequently used by our customers, and again, in case of blocks, we have selected the features that are actually used by our customers and are not likely to lead to non-deterministic behavior of the generated code. In addition to code generation features, the toolset includes a model-level debugger, which is suitable both debugging for ADA and C code and directly observing the behavior of S functions, and also a static verifier, which detects runtime errors and violations of functional properties at the model level. The goal of the D-1 qualification is to demonstrate that code generator faithfully represents the behavior designed in a Simulink model, and thanks to that, the developer is able to reduce the activities that are required on generated source code. There are three main advantages from the qualified code generator. One can bypass completely reviewing the generated source code, assuming that the compliance with requirements and standards is guaranteed by the code generator. Secondly, one is able to bypass low-level requirements-based testing on the generated source code, assuming that the same testing was done on the model level and the code generator guarantees the transformation from the model was lossless. So no information was lost, no behavior was added, and the developer can safely assume that the code behaves exactly as the Simulink model did. There is still some testing required, which is the high-level requirements-based tests, and in these cases, the same tests run on the model can be executed on the target to validate the compiler. And finally, one can bypass coverage analysis on the generated code, assuming that the test coverage was demonstrated on the model, and the qualification process of QGen demonstrates that the model level coverage corresponds to the code level coverage. This last feature is also the basis on assumption of verification that we will do later in this talk. There are a few key enablers for the qualification which I would like to mention. First and most importantly, and probably the aspect that takes most of our time in development, is formalization of the semantics of Simulink and stateflow subset that we have selected, which includes defining the behavior for all the blocks. For this purpose, we have developed our in-house language, which we call block library specification language. It enables us to describe all blocks in a structured way, including the input space, the modes that each block supports, and the code generation rule for each of those modes. Later, the same structured specification is used for developing documentation, developing tests, and verifying mode by mode all the behaviors. We also have specified all the modeling patterns that we enable in the code generator, and this structured specification forms the basis for exhaustive testing of the code generator. The other important pillar of the qualification is hazard and risk assessment, which drives the testing campaign and which lends its techniques from verification of embedded software. So we do careful configuration management, we do independent reviews, and we do exhaustive testing for all of the features supported by the code generator and demonstrate coverage analysis of the code generator source code. Now moving back to the main topic of this talk, the verification of Simulink models. The language behind Simulink model is designed to support robust verification and to be flexible, allowing to easily add blocks to the block diagram language. The model, when built, is verified and validated by simulation. There is no formal semantics of the language, and for simulation purposes, one is not needed. To apply any kind of formal analysis or mathematical reasoning on the model has to be converted to a different formalism, which has precisely defined semantics and which has associated analysis methods. Examples of such tools are Polychrony using the signal language and CocoSim using Lustre. Whenever such conversion occurs, the question is, can we prove that the two models, one in Simulink used in simulation and the other one that was used for formal analysis, are equivalent? Can we actually transfer the conclusions we made on the analysis model to the original Simulink model? Or in other words, can we prove that the two models are equivalent? At this point, I would argue that we can't. We can't demonstrate the equivalence. However, what we can show is the dissimilarity. So we can effectively show that the analysis model or generated source code possesses the same properties than the original simulation model did. And this is exactly what we do in QGen. There are two main activities contributing to showing dissimilarity between the Simulink model and the generated code. On one hand, we demonstrate exhaustively the behavior equivalence of the generated code. As you remember from the beginning of this talk, I claimed that we have exhaustive specification of the input space for Simulink model. Now, based on this specification of all the blocks and all modeling constructs that we support, we construct end-to-end tests and we demonstrate that those tests behave the same on generated code and on the original model. In parallel, we also do structural equivalence of the generated code with respect to the model structure in Simulink, and we demonstrate that the code patterns produced by the code generator correspond to those that we can see in the model. The structural equivalence is done by first human review of the structure of the generated code and that of the model, and secondly, based on the tests that we already developed for showing the behavioral equivalence, we also do the comparison of test coverage. So we demonstrate that the same coverage we can see on Simulink model, we can also see on the source code. One final note before I'm going to demonstrate the actual verification tools. The two tools I'm going to show are both dedicated to analyzing Spark code. So they are specifically for restricted subset of Ada, and for looking from source code viewpoint, they don't help developers with other languages. What we are trying to do here is use the Spark tools to first show that the model is correct, and then with that assumption generate code in other languages such as C and benefit from the analysis that we did earlier. There are several components that contribute to this. First, the QGen architecture. In QGen, we generate code as a sequence of several transformation steps. The very first step is conversion of the input model into something we call system model language, which is capable of representing block diagrams and state models. The model conditioning takes place on that language, and then the conversion to a program is done into another language which we call code model language, which is an abstract program without concrete syntax. The final step of converting to actual source code is in the very end. It's the last step, and it's kept as slim as possible on purpose. The goal is to keep as many transformation steps as possible independent of the output language and reuse them for different outputs. From the qualification viewpoint, we do qualify the workflows both for C and Spark. C qualification with FAA is happening now. Spark will follow shortly. Assuming that we have proven conversion from Simulink to both C and ADA, we can safely assume that the analysis we do on Spark output backpropagate to models also improves the C code generated from the input model. Alright, but now let's have a look at the first analysis tool. The tool is CodePeer, and it's a static analyzer for Spark code based on abstract interpretation. CodePeer finds potential coding errors such as poor buffer overflows and division by zero. It offers 4 verification levels. First one is the most effective, analyzing the code modularly. Fourth level, on the other hand, is exhaustive and sound. If there is potential error in the code, the fourth level will find it, but it also will detect many false positives, so the user of the fourth level must be aware that the results must be reviewed and false positives analyzed. CodePeer produces detailed analysis of each subprogram. A notable feature is automatic generation of pre- and post conditions. So in many cases, the errors are not reported by CodePeer just because the analysis of pre- and post condition determines that the erroneous situation never occurs, so the obvious logic error in a function is never triggered. And also important, especially in current context, is that the tool can be used fully retrospectively. There is no need to add any annotations or any other way to guide the analysis. So in context of model-based development, the CodePeer tool can be used both for generated code and for the external code without explicitly distinguishing them or spending extra effort in annotating or integrating. In QGen context, the QGen Model Verifier change up QGenC code generator, which takes the Simulink model, generates Spark code with predefined switches, then launches CodePeer and stores the results into the result database. Then from the result database, the findings are connected to the model so that the user analyzing the analysis result will get a report in terms of blocks in the original model and will be able to fix the suspicious combinations in the original specification. Alright, let's have a look at simple example. A trivial Simulink model with obvious division by zero in it. Obvious on that small piece, perhaps not that obvious when it was included in a larger model. So let's see what QGen Verifier thinks of it. We launch the command window, select deep analysis, run it, and voila. The analyzer says that we have one medium priority error. Scrolling down, we see that it's divide by zero, and also it identified an overflow check, and in the back trace we can see where the call started from. Now we can go back to the model. We see the block which caused the error. We can also go to the code and inspect the output that is likely fail. And now we can go back to the model, switch off this branch when the input is 0, and launch the analysis again. And here we go. Medium priority error is gone. My model is clear. As mentioned, this analysis doesn't require any tuning from the user, which is a power, and at the same time it's also a weakness of this method. If there are properties that can be derived from the code or from the model, then CodePeer is able to find them. But if finding an error needs extra information from the user, then inside of CodePeer there is no way to give it. And here is another core product that helps us, which is Spark Pro, performing mathematical proof of the generated code. In case of Spark Pro, what I'm interested in is property checking and functional correctness based on pre and post conditions. So based on the program analysis, we can demonstrate that the generated program satisfies its contract. The workflow is similar to CodePeer workflow in QGenV Model Verifier. So we again provide the models. Now in this case, a model decorated with the observers which encode our pre and post condition. We generate again code. We run CNAT-prove on top of it. We get the results, and again we try to connect these results with the original model to go back and modify it until it satisfies the contracts. Let's have a look at another example. This is a simple resettable stopwatch. It has two inputs, reset and toggle. Reset setting the output to 0, toggle putting stopwatch on or off. When it's on, then 1 is added to the previous time. There is an error in this model, but I will come back to that later. The contracts are defined as Simulink subsystems which are decorated by a specific mask telling QGen that this is either pre or post condition, and inside each of those we have a chain of logic blocks determining whether the combination of input and output values was valid and ending in an assert block. Okay, running again QGen on it. Now in this case I choose proof, I execute, and after generating the code, CNAT Studio pops up with a report, in this case reporting that there is a post condition which couldn't be proven, and together with the post condition we also see a counter example. From this counter example I can see that the post condition is not provable when reset is true, and the value of time, the output, is 1. So let's go back to the model. I check my input, must be true, then this branch is taken, and from this branch I discovered that I happened to specify 1 for the constant value produced instead of 0. So obviously the output must be wrong. Changing this constant and launching analysis again gives me a report proof successful, meaning that the error was successfully removed. As you noticed, in neither of those two cases simulation wasn't involved. Obviously for validation purposes simulation is important, but for finding discrepancies in the model I relied fully on formal analysis. There are two main points that I would like to highlight to sum up the benefits and drawbacks of the source level model analysis. From the positive side, we can be confident that what we are analyzing is corresponding to the code that will be finally run on the target. Also, as explained in the beginning of the talk, we don't have to prove two separate conversions for analysis model and for source code. A slight drawback is loss of model level knowledge when going to source code. For instance, block boundaries, implicit assumptions from block interfaces are lost or obscured, and to rediscover them, the analysis tool has to do extra work. To resolve this, we are currently experimenting different ways, like generating additional annotations, giving information about the original blocks, or eventually introducing additional languages to analyze specific properties such as timing. And finally, I would like to remind the key topics that this talk touched. I started from the introduction of QGen qualified code generator for Simulink and Stateflow, converting models to Spark and C, and I explained how this conversion is verified. Then I demonstrated how two of Adacor's verification tools, CodePeer and CNAT-Pro, can be used for verifying models. I also argued that the same approach is applicable to Spark, C, and potentially any other language that will be supported by QGen in the future. Thank you for joining me today.
All right, excellent. Any questions? All right, we'll give another minute or two to see what questions trickle in.
There will be also a kiosk right after this presentation where both me and two of my colleagues will be present and will showcase the tools that were mentioned in this talk.
Tõnu, can you compare it all this with more conventional model checking tools?
No, with more conventional model checking tools, so the approach that I advocated was relying on analysis of the code that will be finally run on the target, which is not something which is frequently done. So usual model checking tool is converting the model to a formalism that is representing only the properties that are verified. And then there is an extra step to demonstrate that the model used in model checking and the source code, they are actually equivalent. So we are eliminating this step.
Thanks.
All right, so yeah, we'll give another minute, see if there are any questions trickle in, and then we can proceed with the briefs for the sponsor kiosks. So. All right. Would you like to go ahead, Adacore? I don't know if that's you, Tõnu, or Tucker, and give a pitch for your sponsor kiosk.
Sure. Hi again there. I'm Tucker Taft, and I've been working at Adacore since 2011 on language design and model-based engineering. Hope you enjoyed Tõnu's talk about Simulink model verification. And as Tõnu said, if you want to ask more questions or see a live demo, of QGen, it's debugger, which is actually pretty interesting in that it's a combination of technology from sort of low-level debugging and higher-level model-based engineering. Please stop by our Zoom kiosk. And the secret password, as hopefully you know by now, is FSW 2021. So other Adacore engineers will be there as well, presenting Adacore's products for Simulink and Stateflow, such as this one, also for C, C++, and Spark Ada. Adacore started about 25 years ago and really just focused on compilers for the safety critical marketplace. But over the past 10 years, we've added higher level tools, starting with static analysis, moving up to formal methods with our Spark-based tools. And as you've seen most recently, our Simulink and Stateflow and soon to be SysML-based model-based engineering tools. So we're going to be presenting and demonstrating Spark, our Spark tool set. It's widely recognized as probably the premier production level formal methods tool suite. It's been used for decades in aerospace and is now we're finding new users in automotive and medical device domains as the level of criticality grows in all of these different domains. And we'll also be demonstrating QGen. You learned about QGen already. And if there's time, we also have our CWE compatible static analysis tool set called CodePeer, which does advanced ADA analysis. It also includes coding convention checkers. It also includes some checkers for C and C++ and a metrics tool. So stop by and happy to demonstrate more of our products. Thanks a lot.
Thanks a lot, Tucker.